Hi, my name is Tyler Kahn, and for my project, I'm going to be talking about quantum key distribution. Specifically, we're going to be talking about the E91 or Ekert 1991 protocol. So, just quickly, what is quantum key distribution and what is cryptography in general? So, even as going back as far as Julius Caesar, when someone wants to send a message through any channel, they have to worry about someone being able to intercept and eavesdrop that message. And so what we do now is we do classical cryptography. So we'll take a message and encode it in that, so only Bob has the key, ideally. And so only Bob can look at the message. And this can be you and your friend, or a hospital sending you private information, or military bases talking to each other. The concept stands for anything. And what we use now is classical cryptography encryption forms like RSA and DES and AES. And these all work on the basis that it's really hard to solve to factor large prime numbers. It's an NP problem. And with numbers so big, you can show that the odds a computer cracks it is infinitesimally small. And it'll take a very long time. But they're all banking on that fact. And when quantum computers start to rise and we have quantum supremacy, we will show that these quantum computers can factor numbers super fast, and they can break RSA and all these other encryption forms. So we need to go to something more reliable. And that's where we have quantum encryption and quantum key distribution, which are forms like BB84 and E91. And so, whereas classical was banking on the fact that it's really hard to solve a math problem, quantum encryption is banking on the fact that no one can violate the laws of physics. So no matter how powerful your computer is, or how smart you are, you can't violate the laws of physics. And so you will know if an eavesdropper is reading your message. And so quickly, the properties we're using, just so anyone can understand, is entanglement is the first one, where two quantum states of qubits, or two or more states of qubits, are based on each other. So here, you can see that knowing the outcome of one qubit will tell you the outcome of another. So there's correlation between the two. And in our case, our qubits are going to be photons. So if I got a photon and I measure it to be a 0, I will know the other photon's a 1, no matter what the distance between the two photons are. An important fact about entanglement that is really useful for the E91 protocol, or any protocol, is that measurement on these qubits or photons will disturb the entanglement. And we'll talk about why that's important. And then the other important fact is the no cloning theorem. And this is useful for any quantum key distribution, which just states that if you have a qubit with an unknown state, you cannot copy it. So I cannot duplicate the photon that Alice is supposed to receive. It's physically not possible because it's going to violate the Heisenberg uncertainty principle. And so that's important because you can't just make a bunch of copies of our photons to see what our key is. But now that we know all that, let's talk about how we set up for the E91 protocol. So first, just to quickly continue on the entanglement, we will have the Bell state of 0, 1, and 1, 0, which is anti-correlated. So whatever I measure or Alice measures, Bob will get the opposite. And you can view this as spin up, spin down, or anything. Anything that's opposite state. And since they're in the Bell state, they're maximally entangled. And we'll talk about why that's important again later. And then, so in each of their respective places, Alice and Bob are going to have 3 different measurement bases. And in our case, we can kind of think about these bases and whatnot states as like a photon polarization. And so Alice is going to have the basis A1, A2, A3, while Bob has B1, B2, B3. And what you can view these as is like 0, 1, which is our Bell state, 0 or 1, 0, we're not our superposition, rotated by an angle of theta. And so for Alice, her rotations are going to be 0, 45 degrees, and 90 degrees. And for Bob, he's going to have rotations of 45 degrees, 90 degrees, and 135 degrees. So these could be like his polarizations. And we can show that, or we can see that they share two bases. So A2 is the same as B1. They're both 45 degrees. And at 90 degrees, A3 is the same as B2. And you need the same basis because that's, if I were to measure my photon in the zero basis, it won't tell me what you'll get if you measure in a different basis, like 90 degrees. But it will tell me what you'll get if we measure in the same basis, if we both use 45 degrees. So that's why you need the same basis for this to work. That's just the property of like entanglement and measurement. So now that we have the setup, how do we actually do it? So just a quick little figure, we'll have a laser anywhere in the world generating these entangled photons. And they'll be sending them through either optical fiber or free space to, again, anywhere in the world, ideally. So here we're sending it to the ECE building and to Suzzallo Library at UW. And then, so Alice and Bob are both receiving these from a third party. And then once they receive them, they have about a 1/3 chance to use the same basis, and then for each photon, Alice and Bob are both going to be randomly and independently measuring their photon with a basis. So each photon gets a random and independent basis. And eventually we'll announce these bases through a classical channel, and we'll show that in an example. And so now that we have about a 1/3 chance to use the same basis, it's obvious that about 1/3 of all bits will be measured with the same basis. And so when we measure them with the same basis, like I said, we will know that Alice will know and Bob will know whatever they got, the other party got the exact opposite. So they can use them for key generation just through flipping it. And even though they don't know what each other have, what each other person has, if they were to know that they measured the same state, like they both measured a 1, they would know that something went wrong. It might be interference by Eve, or it might be a hardware failure or something. But they don't want to say in a public channel, I got a 1 and I got a 0. So what they can do, and why we have all these other states, is they can actually check for an adversary and reveal no information about the bits they've used, because they're going to be checking for an adversary with the bits they discarded. And so with the remaining 2/3 of the bits, they'll calculate S, which is the correlation coefficient. And that's with these calculating kind of these expected values between these different states. And you can kind of see, just looking at this equation, the expected value of any two states or any two like photons measured at a basis is the odds that you'll get spin up, and or spin down, minus the odd you'll get spin up, spin down, or spin down, spin up. So it's kind of the odd you get the same basis with photons measured, or same state with photon measured with different bases. And so once we get S, so this is the Bell's test. And once we get S, we can see what S is. So if we were to get something, an S that's less than or equal to 2, the absolute value of S, that would imply that there's no entanglement. And so why is there no entanglement? That could be, again, because your equipment messed up, or maybe some absorption or decoherence in the atmosphere messed it up, because if you have enough decoherence on your state, it can ruin entanglement. And so either way that something went wrong and you need to discard this key. But if you get an S, absolute value of S that's around 2 root 2, that's good to go. And you can keep your key. And so in real practice, it's hard to get a value exactly 2 root 2, but 2 root 2 is the maximum. So anything slightly less or around it is a good number. And so why this is so good and better than protocols like BB84 and way better than protocols like classical encryption is for a couple reasons. So the first one, like I just said, is that you can do a Bell's test to mathematically show whether something happened and whether your key is safe. And you can't really do that with classical, and you can't even really do that with non-entanglement QKD. So you can mathematically show whether your key is good. Secondly, even if Eve were to eavesdrop, there's nothing really for her to eavesdrop because the photons are being sent in a superposition. So she can eavesdrop, but there's no information to be gained at the moment because Alice and Bob haven't measured anything. So she's really looking for nothing. And third, why it's really important is because the act of generating these entangled photons, as well as measuring them, is truly random. So when Alice and Bob were to measure them, whether she gets an up or down or a 0 or 1 is true random. And no classical computer can do true random number generation. We do pseudo random number generation, which can be vulnerable, but true random number generation, like it sounds like, is random, and Eve can't really crack that either. So you can show this is physically impossible to have an eavesdropper, have an eavesdropper go undetected, I should say. And to just quickly show what S means intuitively, because the two formulas are not that intuitive. If we just look at our Bell state, so in a classical system, we're going to get one measurement. These two states will be one measurement, whatever it is. And so if we just assume those two measurements are going to be 0, 1, or 1, 0, they're anti-correlated. And so that's going to give you a correlation of, -1 and -1. So you get a correlation of -2. And that's where that Bell's inequality maximum comes from. But that's for classical bits. In a true entanglement of qubits, you actually will be receiving 0, 1 and 1, 0. So since we know that 0, 1 or 1, 0 is going to give you a correlation of 2, we can say that 0, 1 and 1, 0 will give you a higher correlation than 2, specifically 2 root 2. So that test is really showing whether there's been entanglement in whether your photons were truly entangled when they were received and measured. And so that's why it's such a good test, because it can show you whether you are receiving superposition of entanglement, or entangled photons in superpositions. And so now we can kind of see a quick demonstration. So Alice wants to send a message to Bob, and so she's going to want to generate her one-time secret keypad. And so she'll turn on her laser, and she'll get entangled photons, and let's say she'll get down, down, up, up, down. And Bob's going to get the exact opposite, up, up, down, down, up. And so now they're going to measure their photons in a random and independent basis. And once they've done that, they will say what basis they measured in. So she'll say, I used basis A1, A3, A3, A2, A1. Well, Bob's going to say, I used basis B1, B2, B3, B5, or B3. And what's important is that even this is technologically very hard, But Alice and Bob are synchronized. They're so synchronized that they know when to expect photons. So if Bob does not get a photon, instead of just everything being shifted, he will just say, I did not get a photon. That could be because of like absorption or something. And so they'll just ignore photon number 4. And then Alice and Bob we'll say, look at, oh, A3 is the exact same as B2. So we'll keep photon number 2 for our key. Photons number 1, 3, and 5 we'll use for our Bell's test. And so then Alice can say, they know what measurements to use. And Alice can say, okay, in photons 1, 3, and 5, which I'm not using for my secret key, I got up, up, down. And Bob will say what he got. And then they will do a Bell's test to see whether these photons were entangled. And if they were entangled, that means there was no issues and they can keep the key with the remaining 1/3 photons. And if it was less than 2, that means they need to do this again. And then once they get the key, Bob will have the exact inverse of Alice's key, and he can just flip it to get Alice's key. And now they can just do binary addition to encode and decode a message that will be sent through a classical channel that Eve can look at, but she cannot interpret. So are we actually seeing this stuff used? Yes, we are. So the Mesius satellite, which is a Chinese satellite, and China is really leading the pack in all of this. They do a lot of BB-84 with this satellite, but they've also done E91, which is much harder. So in 2017, they did a breakthrough of 1,000 kilometers. And it was with a satellite that had both a measurement device as well as a laser. So Alice is in the satellite and Bob is down in the telescope. And they received a secret key of about 3.5. And then in 2020, they did the exact same thing, except now they were both on Earth. So here Alice is in one telescope in part of China, and Bob's in a different telescope about 1,100 miles apart in a different part of China. And they got a quantum bit error rate that's usable, but their secret key was pretty low. And satellite to Earth communication is definitely more promising at the moment because most of it is going to be sent through the vacuum of space where you really don't have to worry about much. You only have to worry about in the atmosphere when you have stuff like absorption and turbulence and other light. But if you send it through something like optical fiber, the loss on it is so much higher than in free space that a number like this is like, at the moment, it's theoretically impossible. And so what technology do we need to do to really bring this to a commercial scale or bigger scale? Is, like I said, we need improved distance and improved time. So going back here, well, 1,100 kilometers is very impressive. It's not feasible right now to do something like China to US or the moon to US or Mars to US if we ever, had bases on different planets. So those are 10,000 or hundreds of thousands of kilometers. In addition, 0.12 bits per second for a secret key is really bad. I mean, if you had a secret key that was 1,000 bits long, this would take over 2 hours to send. So we need to improve that. And so how can we improve that? So improving optics as well as the post-processing and real-time processing is a big step. And the big step that went from 2017 to 2020 was the telescopes got improved a lot. And we can improve the telescopes again, and we can do stuff like atmospheric correction with adaptive optics. In fact, there's some work at the Air Force Research Lab that shows that with such good adaptive optics, you can even send this stuff in the daylight. And I'll talk about that in a second. So stuff like atmospheric correction, and a lot of it is just we have to correct for the noise. Improving our telescope lenses is helping. Quantum error correction code is going to help a lot. and something like, because we already have classical error correction code, and now we need to go to quantum error correction code. And I believe the 2020 Mesius paper used Hamming code, and they could easily improve their bit error rate with something like low density parity check coding or turbo codes, which are much more higher level error correcting codes. In addition, there's something called a quantum repeater, which is like, we have classical repeaters where we just duplicate our message and relay it, but because of the no cloning theorem, it's harder to do that. So we need to find out more advanced ways of storing like helper photons and using quantum teleportation, which we have, but it's very, it's not very mature technologically, and definitely not for like real commercial use. We also need to, whoops. Sorry, we also need to improve the device, which kind of goes back to improving the optics and whatnot, because even though E91 is theoretically perfect, we have flaws because we have imperfect hardware. And so while Eve can't violate the laws of physics, she could exploit either our telescope or our receivers or our transmitter or something. And also, in our kind of like non-ideal settings, the Chinese tests were done at like 2 a.m. with really clear weather, which is, you know, if this were to become big scale, you would have to be able to do it at much more random and organic times. So with improving our devices, not only will our theoretical security go up, but we'll also be able to do it at any time. Because right now, even though, like I said, E91 is perfect, we have so much, there's so much error rate in them, and that it's kind of hard to say if we could actually use the key, because the keys need to be the same. And so stuff like I said, quantum error correction code and improving the optics and real-time adaptive optics will help reduce the noise to make it much more secure, as well as let us do it when it's possibly cloudy or in the daytime. And quantum repeaters will help make fiber optic much more viable so that we don't need to use satellite communication. And so lastly, do I think we will see this technology in the next 10 years? I think we will. I don't think, at least not for a long time, someone like me or you will be able to just bust out our quantum key generator and use the Mesius satellite. But I do think that something like the government or big banks or something will use this. China is actually, by 2030, I believe, they're planning to have a fleet of BB-84 satellites and to have all of China use that. So I think that entanglement satellites will be the next thing to come. It's just like the technological next step. And entanglement satellites are also very useful because of something like quantum computing, where it's very hard to go from 50 qubits to 100 qubits, but through quantum distributed quantum computing, you can maybe utilize two computers that have 50 qubits. So I do think quantum entanglement communication will arise in the next 10 years. And because of that, E91 will just be one of the many uses of it. And maybe a place like the US, who doesn't have much now, will make that jump directly to E91. Whereas a place like China, who already has so much BB-84, might be hesitant to make a much smaller jump. So that's just my thoughts on the scalability of this in the next 10 years. Those are my references, and thank you.